Log on, tune in, find out. Another good idea from Cambridge.
Are you ready to start?
I'm ready, yeah. I'm going to say something.
Okay, so I'd like to introduce Andreas Kirsch from Karlsruhe Institute of Technology, and his title is Factorization Method for Electromagnetic Inverse Scattering Problems.
Okay, thank you. Yeah, first I thank the organizers for the opportunity to give a talk here. And this talk will again be on the factorization method. Last week I gave a course on the method for a model problem, for a much simpler problem. And today I want to talk on the factorization method for Maxwell's equation. And there appear some problems which do not appear in the scalar problem. And I want to point out these difficulties we still have to justify the factorization method for this case. So my talk will not only be on the factorization method, but also on the related interior transmission eigenvalue problem. Whenever there is a scattering problem in frequency domain, there is a corresponding eigenvalue problem which goes with it. So also for this problem there is an eigenvalue problem, and the second part of my talk I will say something about that. So this is the outline of my talk. First I formulate the direct and the scattering problem. I collect some information and some properties of the far field operator, which is built from the scattering amplitude. Then I explain the factorization method and show you, I do not go into the proof of course, but I show you the essential difficulty or why we have to make some assumption there. And in the fourth part, I will talk on this interior transmission eigenvalue problem, show you how you can prove, in this case, discreteness and existence of real eigenvalues. So the scattering problems, so I look at a non-conducting medium, so the conducticity is 0, and epsilon r is the background permittivity times the relative part, which depends on x, and it could be matrix valued, so it's an anisotropic medium there, but it is 1 outside some bounded domain, and it's symmetric, and I will make a further assumption on that later on. Also, the permeability has the same structure, and mu r is an L infinity function on d, and omega is the frequency, and then the incident wave satisfies the Maxwell system in the frequency domain, and in all of my talk I consider a fixed frequency. I'm not changing the frequency omega. And then the scattering problem is determine the total fields E and H, which satisfy now the Maxwell equation with mu 0 replaced by mu and epsilon 0 by epsilon, and such that the scattered parts, so the difference between total field and incident field, satisfy the Silver-Müller radiation condition. So I wrote it this way. Maybe it's better to divide that through the modulus of x. Then you see that far away the magnetic scattered field and the electric scattered field are almost orthogonal. So when you look back here, it's a matter of taste how you treat that. I prefer to work with one of the fields, E and H only, and so I've chosen here to work with a magnetic field, and so I eliminate the electric field from the system here. See, if you take the inverse of epsilon r to that side, then there's I omega epsilon 0 is constant, so you take the curl of this part and then plug in there, then you get this Helmholtz equation, or this type curl type in this form, where here the inverse epsilon r appears and here the mu r. And the wave number now k is omega over square root epsilon 0 mu 0. Okay, of course, the solution has to be understood in the variational sense here. So the correct space to treat that is the local Sobolev space H curl in R3. That means in every ball, the solution H is an L2 function, and also the curl is an L2 function for every ball of finite radius. And then you multiply with the test function here and does kind of partial integration. You end up with this equation, and that holds for all test functions with compact support. That is a way to understand the this equation here. And so I don't want to say much more about the direct problem. The way you solve it, there are several ways to solve it. First of all, what you can prove under these assumptions, I mean, essentially, you need that epsilon r minus 1 is kind of positive, and mu are also positive, not in the case you mentioned previously. Then it is not difficult, or the standard, to show that you have this kind of Fredholm property that uniqueness implies existence and continuous dependence. The problem is really existence. Existence relies on a unique continuation property of this equation here, of Maxwell equation, and at least to my knowledge, this is only known under some smoothness assumptions on epsilon r and mu r. And so one of the standards references is a book by Peter Monk, the first part, which is not concerned with the finite elements, but with Maxwell equation. Okay, so I don't want to say much more about the direct problem, except that outside the domain D, we have that the magnetic field solves this equation. Remember, the epsilon r is the identity and mu r is 1, so outside is this. And also is a radiating solution, satisfies the Silver-Müller radiation condition. And then one can show this asymptotic behavior as the modulus of x tends to infinity with this spherical wave sitting at the source at the origin. And this is far field pattern, or scattering amplitude is that called. My favorite, just one sentence, my favorite method to prove this part A here is to convert this problem to integral equation or integral differential equation of Lippmann-Schwinger type. That is a very nice way. You can also do it for L infinity function there, and then you see this property. For example, this property you see immediately, because outside you look at the fundamental solution and the asymptotic behavior of the fundamental solution, and then you get that. Yeah, and this vector field V infinity is a tangential field also. You see that also. Sorry?
That must be plane wave.
Yeah? No. That is here. That is.
You say Lippmann-Schwinger and so on.
Yeah, it does not have to be a plane wave, Lippmann-Schwinger. It's an integral equation. You can have arbitrary source term on the right-hand side. We discuss. I can show you. I have it written down, and I can show you that. But this is the reason why I mentioned that. That is for Lippmann-Schwinger, that is well known in the scalar case. But here, for arbitrary sources, that is maybe not so well known. But I don't want. That is not the topic of my talk here. So now, I look at plane incident fields of direction theta hat. Oh, by the way, my hat, x hat and theta hat, that always indicates unit vectors. Yeah, the hat is always a unit vector. So if you have an incident plane wave in this form, and then of course the electric field has this form, such that the P is orthogonal to the direction of incidence, then they solve the Maxwell equation for the incident field. And because the scattered field then satisfies this outside some ball and is radiating, the scattered field had that kind of expansion, and the far field pattern here does not depend only on x hat, but it depends also on the angle of incidence and on the polarization vector, and of course also on frequency. But I do not vary frequency, so I do not indicate the dependence on the frequency. Okay, So these, okay, now you are set aside, very good. So the inverse scattering problem, many of you have seen this picture. It's one of my favorite pictures here to introduce that. That is now the corresponding two-dimensional case maybe in H mode, where you have a scalar problem, and this function here depends only on two variables, the angle of observation and the angle of incidence. And here I have plotted the real part and the imaginary part of these scalar functions for one example and for the other example. And the inverse scattering problem is, I give you this picture. This contains, this is just a plot of the far field pattern with respect to these two angular variables. And you want to determine D. That is the inverse problem. You could phrase, of course, the question determine not only D, the support where your permittivity differs from the background, but also the epsilon r and the mu r themselves. But we learned from the talk here on non-uniqueness that in the tensor case, epsilon r is a matrix. By a change of coordinates, you do not expect uniqueness at all. So we are modest, and the factorization method only determines the support D of that, so the shape. But we don't have to know epsilon r, the values of epsilon r, as we will see. Okay, so now we, in the second part, far field operator very briefly. First, you have this famous reciprocity relation. So if you observe from the other direction and have these incidents and you interchange observation and direction, then you get the same thing here. It's not, for our purpose, not important here. Notation L2T means that now the tangential vector fields on the unit sphere. The tangential T means tangential vector fields on the unit sphere. And the far field operator F is just the operator which has our data as a kernel. So this is our data. Maybe I did not say that clearly. The data is that we have the far field pattern for all angles x hat, for all directions theta hat, and for all polarizations. That means because you need it for three different polarizations, and you have it for all because it's a linear with respect to p. So this is a far field operator. It's apparently linear. It's a normal operator because we have no absorption here. Sigma is 0, so it's normal. That means F commutes with F star with its adjoint, and the scattering matrix S is the identity plus some factor which depends on the normalization. Is a unitary operator. These are important facts for the following. And first question, and that is has been introduced by John Sylvester, and also you mentioned that. First question is, when is F 1-to-1? Or in other words, when is 1 an eigenvalue of the scattering matrix? And then you have the theorem, very easy to prove, and you have seen these kind of proofs in the previous talks. The F is 1-to-1 if and only if there exists no non-trivial pair UW in this L curled spaces in D, now in this the inner inside outside duality. Physicists call that sometimes, because F relies on the outside. The scattering problem is outside of D essentially, while this problem is inside of D. You have this equation, which is the total field. You have this equation, which is satisfied by the incident field, and the Cauchy data coincide in this way here. The Cauchy data are just that the tangential, nu is the normal, the normal vector at the boundary, so that the tangential components coincide, and this corresponds to the Neumann boundary condition there. This is only the if, and not the only if. There is some part missing, such that this the solution here can be extended also to the outside of D, and in such a form that it is has a form of a Helmholtz field of that form with some p in this L2 space. and then it's an if and only if. Okay, so that gives you, and this theorem is true for all of the scattering problems. You know, the far field operator is injective if k square is not an eigenvalue of this corresponding eigenvalue problem. I just want to remind you, if you have a perfect conductor and do scattering by a perfect conductor, then the corresponding eigenvalue problem is just the ordinary electromagnetic eigenvalue problem inside of D with the boundary condition, homogeneous electric boundary condition there. Okay, now we come to the main part of this talk, the factorization method. I assume that D is open bounded with, it does not have to be that smooth, but that is not an important point. But the important is that the exterior of D is connected. D itself does not have to be connected. It could be consist of different components, but no holes inside. This is the point here. And this assumption now here, the inverse, which appears in my differential equation, is a background identity plus Q, and Q is a positive, uniformly positive definite on D. So it has a jump at the border, at the boundary of D. The μr is now, so that means Q is bigger than 1. That means that epsilon r is less than 1. Also Q is less than 1. There are restrictions. If you interchange here minus and there plus, it also works. But the same sign plus plus or minus minus does not work. We don't know. This is one of the open problems there. So you have this you have this situation here, and Q is outside. It's 0 outside, and here it's non-negative on that. Unfortunately, we have to make another assumption on mu, which is very nasty. And that is, of course, clear. I mentioned that this equation with the source term here, now I have two source terms, one of curl of an L2 function and an L2 function, that this has always, for all f and g, a unique radiating solution. That requires, some smoothness of epsilon r and mu r. The unique continuation property is, the uniqueness of that is a problem, not the existence then anymore, because we have this Lippmann-Schwinger type equation for that thing. Okay, so this is not a serious assumption. You have to make these kind of assumptions. These are more restrictive here, there. So the goal is now determine the support of Q from the far field pattern. So I just want to go a little bit into the derivation there, but only briefly. So this is a total field. The total field satisfies this. If you write H as a sum of the scattered and the incident field and use the fact that the incident field satisfies this equation for Q equals 0, then you end up that the scattered field satisfies this inhomogeneous equation with this source term there. Now this is a special case of this type here. The reason why I put a square root of Q here is explained later. So you have curl Q times some function, so F1 is a curl and F2 is k square root of Q H inc. Okay, so, and this, so now you define an operator A which maps things which are in the far field, so L2 space, into this product of these L2 spaces by just taking your P here and you build this Haglot's field, P and WP, and you take here in the first component the curl, in the second case square root of Q there. Okay, and now this is the first theorem which appears always in the factorization method. You kind of link the determination of D by asking or by the range of some operator. So take this function phi z. For every z you can define that on the unit sphere, explicitly given, and then you can prove that the point z is in D if and only if this function is in the range of R star. So remember, A is given by very explicit, I mean if you substitute in, it's an integral operator on S2 evaluated on D. So the the adjoint is a volume integrate operator of that type, and what you can easily see by looking at the asymptotics of the fundamental solution here and there, that the adjoint of A star is just the far field pattern of this thing here. And Vz, this is a far field pattern of this point source sitting there. Yeah? So you have to look, is it possible, you know, to find F1 and F2 such that this is equal to that? And this is possible if and only if the point is inside, because if the point is outside, then you see that this is the fundamental solution is singular at Z, so there has a point, a singularity outside of D, but these functions are regular outside of D. No? Their singularities are inside of D, so they cannot have a solution. So that gives you the proof of that. And now, if you use this operator A and the A star there, you can factorize F in the form minus A star T A, where now the middle operator T is given by this form, F1, and V is a solution of that source problem I've shown you before. The details are not so important. Here I have it again. The T is given by that, where V here solves this source problem, right? And now the factorization method needs assumes some properties of this operator T. In particular, the most important is T has to be the sum of a coercive and a compact operator. It's not difficult to see that T is invertible, but that is not sufficient. T must be the sum of a coercive and a compact operator. And this is difficult to show. The theorem, I can only do it under the assumption that the square root of Q, which appears here, is a C1 function up to the boundary and vanishes on the boundary. That's really kind of bad if it is really going down. It could go down inside as well, but at the boundary. So the case that Q is constant is not settled in this case, unfortunately. I need that because of this. Really, it's a pain with this Maxwell equation that this H curl space is not compactly embedded in L2. So you have to have some knowledge on the divergence as well, and of the normal component of the function. And that's the reason why we have to make these I have to make this assumption here. And then, and if you find in this operator, this is coercive, and the difference between this and that operator, which then is compact, where Vi is now the corresponding equation here for k square is I times some rho. Rho is large enough. Okay, further, second assumption, which is not very crucial, but also shows you that the interior transmission eigenvalues appear here. The imaginary part of this quadratic form here is positive for all f in this, provided k square is not an interior transmission eigenvalue. So this assumption does not only appear for the injectivity of f, but also here. And these are the two essential assumptions for the factorization method to hold. And then the so-called range identity tells you if that is the case, there under these assumptions I mentioned, the range of H star is a range of f star f to the fourth. Yeah? So remember, H star is explicitly expressed by D, and D is unknown. So we don't know H star, we don't know the range of H star. But if we had that before, that Z in D, if and only if this function is in the range of H star. So by this, we can conclude that Z is in D if and only if this concretely given, explicitly given function is in the range of f star f to the fourth. F is known. No? F is known. This is an integral operator with our data. So this is a explicit characterization of D under these assumptions I mentioned. And if you take a spectral system of the normal operator F, then you can, of course, express the range condition in form of a Picard criterion, in form of a series, so that the Fourier coefficients of this function with respect to the spectral functions there decay fast enough in order that this series converges. Okay, so what you do is here this is my book, but this part here for that case includes a mistake, a very nasty one. But I corrected it on my homepage. So so I want to show you some simulations here in 2D now. What I do is I take the inverse of the series. Remember, Z is inside. If and only if this series converges, that means the inverse gives you a positive number. If Z is outside, then this diverges. This is infinity. 1 over infinity is 0. The blue color is 0. You know, and so I for every Z in space or in a large enough region here, I computed this series, but in practice, of course, a sum. I had 32 incident angles, 32 observations. So instead of the matrix, the integral operator F, I have a matrix, 32 times 32 matrix. I do a spectral decomposition once in the beginning, and then it's very, very fast to compute this sum here. This is sum of 32 points, and here's just a multiplication of two vectors there, you know, and then you get this result. And here you see that is a picture of the plot I gave you at the beginning of the section. You know, here you see apparently the scatterer consists of two different objects, and this is a kite and this is a little ellipse. This is without data, 32 times 32, but no noise on the data. And this is with 5% noise on the data. And I just have some more. Here is a different wave number. This is it's a triangle, also with more or less data. And this is an example from real data. That is an aluminum triangle, and a long time ago somebody put that into the net without telling the people what it was. You know, they just said it's an object of aluminum, and try your favorite method to determine the object, and so the factorization got this one. Okay, last part of my talk will be on this interior transmission eigenvalue problem, and I want to show you an approach which is similar to the one John gave yesterday at the beginning of his talk. So this is joint work with Fioralba Zacconi from the University of Delaware, and she will talk on this after me. So recall the interior transmission eigenvalue again. Here, instead of k square, I wrote lambda now. These are one equation, the other equation, and these are the Cauchy data there. And I make here again the assumptions. Unfortunately, they don't fit the assumptions of the previous part. The assumptions on Q are the same. But here, on the matrix Q, which is sitting here, but here we have to assume that Q is constant. So, I treat here the case that Q is a positive constant. So I really have that term here. But in my previous part, I had to assume that Q is smooth and goes to 0 at the boundary, which is apparently not satisfied here. Okay, now now we come back to David's talk. Here we look at an example, and even easier example here. Q is just P times the identity, and P and Q are constants, both. Then you can, these 1 plus Q, which came here, is a constant, so you can divide through, and so you end up with this equation where this is a constant and here is this corresponding constant 1. So that looks like the standard transmission problem, but here you have this different Cauchy data here. Here's a factor still there. But nevertheless, I mean, you know what solutions are here. For example, take any n and look at the spherical wave functions for that problem here. So alpha times the curl of this spherical wave function with kr. K is the square root of lambda here corresponding to this one. And here is a spherical wave function k rho r. Rho is the square root of this here. Yeah, and then this is solved, and this is, if you match these boundary conditions, that gives you a system of two equations, and you again do the expansion for large values of k, and then you see they oscillate asymptotically, and it gives you existence of eigenvalues. I mean, it's just the same way as we have seen that in the previous talks. But as you will see, it is important for the following. We have to use that. So in the scalar case, I'll just recall what John did yesterday. In the scalar case, you have this Helmholtz equation type with that, and what you do is you look at the difference between u and w. My notation is a little bit different. Here it's v, and u is interchanged with respect to John's talk. Then v satisfies two boundary conditions. Cauchy data of v are 0, and w contains no boundary condition. And they solve now, v solves now this source with a source here and w there. So then you divide by lambda and q, and then you have your w, and apply this operator here again to that, and then you have eliminated v, and you get a fourth order problem with the correct boundary condition. Cauchy data vanish. And yeah, he looked at the at this unbounded operator with the Laplacian matrix form. I prefer to work with the Green's with the inverse of that essentially. So if you look at the variational form in Lax-Milgram, you see that if you take the proper inner product here in L2 here, Laplace with this weight 1 over q, then you see that this can be written in the form of L lambda v equals 0, and this operator Lk maps this space into itself and has this depends quadratically on lambda. Okay, and then from there you see already applying analytic Fredholm theory, for example, that the spectrum is discrete, and also you can prove existence, and that will be done now for the Maxwell case. Again, we set v w minus u, but then v has 0 boundary condition in the way that the tangential component of v is 0, that is h0 curl, and w, and they satisfy now this equation. And here it's more complicated on the right hand side, no? With respect to, here you had a very simple right hand side for v, and you could explicitly eliminate w. Here you have a more complicated right hand side, and it's not so clear how to eliminate w in this case. This is the second equation, and also v has satisfies two boundary conditions. One is contained in the space, and the other one is given here. Okay, so now here we have to make the assumption that q, or use the fact that q is constant. From here you see, if you take the divergence of that equation, you see that because the divergence of w is 0, divergence of curl is 0, therefore for lambda not 0, the divergence of w is 0, and then you see also from that equation that also the divergence of v is 0. So we can restrict ourselves to the divergence-free fields. And this is not possible if q is not constant, and that is the main reason why we couldn't do that in the more general case. Yeah? So my x hat, x0 is the space of V. This is just a weak form of saying that the divergence is 0. Yeah? But no, the normal derivative of V is not 0 in general. The normal component, sorry. Okay, now just as before, we define this operator L lambda. How do we do that? Yeah, look at that. Look at that. Now we take the we take any V in the space and solve for W. We cannot do that explicitly, but we can do it implicitly as solving this problem. Given that, I can solve for W. No? So here I just, given V, I can solve this. This is a Neumann type boundary condition, a boundary value problem. Yeah? And here we need also the correct signs of Q and Q, otherwise we run into problems. But these are the correct signs. This is a Neumann condition, and that is the differential equation. So that gives you my V depending linearly on V. And then I look at that form here. If that is 0, then that means that W satisfies this curl square minus lambda W equals 0 by partial integration. That's the weak form. So I take that as a linear functional, and my Ries representation, I call that Z, V. So then I have a mapping from V into ZV, and that gives my operator L. And you can, if you do it more carefully, you can define that lambda L not only for positive real, but for all complex lambda with real part bigger than minus delta for some delta positive, up into the negative real plane. And then you can first prove the equivalence. If you have an eigenvalue and you define V to be the difference, then L lambda V is equal to 0. And if you have a V which satisfies this, and W is the solution of that problem I mentioned, and you said U W minus V, then this is an eigenfunction. So you have an equivalent there again. And also now these lambda L lambda are self-adjoint for all real non-negative lambda, and they depend analytically on lambda for these things. So, and also L0 is coercive, and you can prove this part here. And here you see why we have to restrict ourselves to this space with divergence-free fields, because if you plug in here a gradient, then you don't have coercivity anymore. Actually, the gradients are exactly the kernel of L0, are the gradients of scalar functions. So, but on that space, this is an equivalent norm, so we have coercivity of L0, and now we can, as a corollary, write this in the form of, in this form, and this operator is compact, and so we can apply this analytic Fredholm theory, which gives you most accountable number of eigenvalues. And just one more or two more slides. Also, you can do the proof by Lassie and John, and Gentiles, Zacconi, and Hadar on the existence. So the idea of the proof by Lassie and John was it is sufficient to find some function v hat and some lambda hat such that this quadratic form is negative or not positive. Then the smallest eigenvalue of L0 is positive, because L0 was a positive definite operator, and the smallest eigenvalue of L lambda hat is non-positive, because you have this you have found this v hat, such that this quadratic form is negative. And then the continuous dependence of the smallest eigenvalue on lambda gives you a lambda such that the smallest eigenvalue is 0. And so you have at least the smallest one eigenvalue. But then the Right, and so they, in their paper, they proved it for sufficiently high contrasts, and the idea of Zacconi, Gentides, and Hadda, it's a very ingenious idea. You take a ball inside of D and an eigenvalue lambda hat, which corresponds to that ball, and constants Q and Q0. Q0 was a lower bound on my capital Q. So now I go back to my example. If B is a ball and you have constant parameters, then there exist eigenvalues. So there exists an eigenvalue corresponding to these constant in that ball. And this function V hat is first of all in H curl of B, but if you if you extend that by 0, then it is in that space H0 curl of D. And then you take the projection onto this subspace of divergence-free fields, and then you can show by some estimates that you get, again, this satisfies this condition. And if you take not only one, but you take several balls in that D, then you can also prove existence of infinitely many eigenvalues. Okay, some references, not complete at all, but I can really recommend this paper because all of them are here. And this is kind of a service paper till 2007. That was before existence of eigenvalues have been proven. No? So I did not write anything before that because this is the paper. And then this was the major step forward in proving existence, paper 2008. I did it for the Maxwell equation. That's the reason why I mentioned my paper here. And then another step forward was to remove this assumption there. And this paper, actually 2 papers of that, but I cited only one. And the talk itself is based on this joint paper with Fioelba. Okay, I thank you for your attention.
Time for a few questions. Maybe after the whole week. Thank you again.
Okay.